Good morning, students. So, in the electrostatic, in the first part, electric charge. mm, So, today we will see the very important Coulomb's law in electrostatic. Coulomb's law in electrostatic. Okay. So, we say like charges repel each other and unlike charges attract each other. But this physics is a science of measurement. So we require with what force the two like charges are repelling each other. With what charge two unlike charges are with what force two unlike charges are attracting each other. The exact measurement of the force is must in our physics. So since we completely depend on the measurement. So for that, mm, scientist Augustine Coulomb, so through a torsion balance, he found different the force different between two different charges. If like charges, with what force they are repelling each other. A sensitive balance, a torsion balance is a sensitive balance to measure the force. The force of repulsion between the like charges. Different magnitude charges he has taken under different conditions in a different temperature, pressure, uh, medium. He has conducted the experiment. He conducted the experiment. So he tried to find the force between two charges. It may be like charges, unlike charges. The force between them he tried to find. In by doing many number of experiments. What conclusion he has drawn there? What conclusion he has drawn there? So first, the force of attraction or repulsion between point charges, between point charges. Hmm? So force of attraction or repulsion between point charges. So first thing what he has noticed is it is directly proportional to directly proportional to product of the charges, product of charges. inversely proportional to inversely proportional to square of the distance between them. Square of the distance between them. You can see it is very analogous to our Newton's gravitational law. So where we are finding the gravitational force of attraction between the two masses. So that force of attraction, there it is only force of attraction, is directly proportional to product of the point masses. Product of the point masses. And inversely proportional to square of the distance between them in our Newton's gravitational law. So in electrostatic, it is very much analogous to the same Newton's gravitational law. Coulomb's law is analogous to electrostatic here, electric charges here. So what it says, this force is directly proportional to product of the charges Q1 and Q2. If Q1 and Q2 are the two charges, so whose force of attraction or repulsion you want to find out, force is directly proportional to product of the charges, and force is inversely proportional to square of the distance between them. Square of the distance between them. So that is why we say this as inverse square law. Inverse square law. If it is like this, any one quantity is inversely proportional to square of the distance. So if it is like this, we say it as inverse and square. This force is inverse and square. Our gravitational law is also a inverse square law, and Coulomb's law is also a inverse square law. It is inverse square law. Okay. So force of attraction or repulsion between 2 point charges. See, point charges, they should be zero size. Point charges means the size of them is negligible. They should have zero size. If not zero size, compared to the separation, the size of the, compared to the separation, the size of the charges should be negligible. In fact, we say them as zero size. Point charges in the sense zero size. They should not have any size. When zero size is not possible, at least compared to the separation between the two charges, compared to the separation, the size of these charges must be very, very negligible. Size of the charges should be negligible. Then such charges, we say them as point charge. Okay. So now, when we combine these two, what is? This is our one charge. This is one charge. I say this as charge Q1. This is other charge, charge Q2. They are separated by a distance d. They are separated by a distance d. So then, what the this Coulomb's law says? hmm, Force is directly proportional to Q1 and Q2, and force is inversely proportional to square of the distance between them. So when we combine these two, I can write it as force is directly proportional to Q1 into Q2 by d square. Force is directly proportional to Q1 into Q2 by d square. So this proportionality sign, as we have been doing, proportionality sign we change to a proportional constant. That proportionality constant I said C here. Proportionality constant C. It is Q1 into Q2 by d square. This is our Coulomb's law. And this force we set as Coulombian force. We can say it as Coulombian force, a force of attraction or repulsion. We say it as a Coulombian force. In a CGS unit, this proportionality constant, in CGS unit is equal to 1, because when he has derived this expression through by conducting many number of experiments with different magnitude charge in different conditions in a different medium, so when he conduct, so this proportionality constant he has taken as equal to 1. How we were doing in the case of Newton's laws of motion, F is equal to ma. F is equal to kma, in fact there. In SI unit, that k value is equal to 1 we take while proving F is equal to ma. Very similarly, he has taken in CGS unit, he has taken this C value as C value is equal to 1. But when we convert it into SI, this charges, unit of charges, distance, force, all these we have to convert. So during that time, what will be the value of this proportionality constant? We will see. In CGS, it is that constant, proportionality constant is equal to 1. What happens? What will be the value in SI unit? So that we will see. Okay. Same. CGS unit of charge is stat Coulomb. In fact, there also we have two types. Whenever we electrostatic, all these we say, there we have electrostatic unit and magnetostatic unit. ESU, EMU we say in CGS, electrostatic CGS unit. Magnetostatic CGS unit, electromagnetostatic we say, EMU we say. So here ESU unit, ESU. So it is a stat Coulomb. Celsius unit of charge is stat coulomb, and 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb. 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb. Electrostatic Celsius unit is stat coulomb, and 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb. So now this whole thing, this force, charges, and this distance, all these, now I want to convert it into SI. So then what will be the value of this proportionality constant in SI? We will see. So now charge. So when 1 coulomb is equal to 3 into 10 to the power of 9 stat coulomb. So here it is in stat coulomb, that I have to convert into coulomb. So this will be 1 by 3 into 10 to the power of minus 9. So in fact he has taken in stat coulomb, that I am converting into a coulomb. So then distance he has taken in centimeter. If I want to convert it into, it will be 10 to the power of minus 2 meter. Force 10 to the power of minus 5 Newton. Dyne I have to convert. If you substitute all these values, in this, what it is? Force is, it is 10 to the power of minus 5. It is equal to C into C dash I will take, because that I want in SI now. C dash is, this is 1 by 3 into 10 to the power of minus 9 into 1 by 3 into one more charge, that also I will convert into 10 to the power of minus 9 whole divided by 10 to the power of minus 2 whole square. Or the CGS units I want to convert into SI. So C dash will be what it is. Okay, I'll make it like this: 10 to the power of minus 5 into this I will take here 10 to the power of minus 4 is equal to C dash. It is into C dash into, so 10 to the power of minus 9 into 10 to the power of minus 9 whole divided by this 9. So 10 to the power of minus 9. So 10 to the power of minus 9 get cancels. Okay. So C dash will be C dash is equal to, I can write it as 1 by 9 into, if this is brought down, 10 to the power of 9. So C dash, in fact, it is the C dash C dash into. So if you take it this side, what it will be? C is equal to 9 into 10 to the power of 9 C dash. 9 into 10 to the power of 9. In CGS unit, he had taken as proportionality constant as 1. In a CGS unit, proportionality constant he had taken as 1. But that proportionality constant in SI, if we convert, that proportionality constant is coming out as 9 into 10 to the power of 9. In CGS it is 1, whereas in SI, its value is 9 into 10 to the power of 9. Okay. So therefore, if I so how can I write now? Coulomb's law. Coulomb's law in electrostatic. Coulomb's law, how can you write? In SI, how can I write this? So F is equal to proportionality constant here. It is 9 into 10 to the power of 9. 9 into 10 to the power of 9 into it is Q1 into Q2 by D square. So Coulomb's law in SI is F is equal to, so this is our proportionality constant. In CGS it was, in CGS it is F is equal to, since the proportionality constant is 1 into Q1 into Q2 divided by D square. In CGS we have just it as Q1 into Q2 by D square. The same thing, if you convert in SI, you will get it as 9 into 10 to the power of 9 into Q1 Q2 by D square. So this 9 into 10 to the power of 9, rather than keeping it in the same way, in the numerical, so rather than writing it in the same way, so which gives the same value as 1 point, as 9 into 10 to the power of 9, what it is? It is a 4 pi epsilon naught. So which gives 1 by 4 pi epsilon naught value, gives the, when you calculate, gives the value of 9 into 10 to the power of 9 for in vacuum. So instead of writing 9 into 10 to the power of 9, they have written it as 1 by 4 pi epsilon naught Q1 into Q2 by D square. So 1 by 4 pi epsilon naught value is 9 into 10 to the power of 9. So this becomes your Coulomb's law in SI. In System International, Coulomb's law is 1 by 4 pi epsilon naught Q1 Q2 by D square. So this epsilon naught, we say it as permittivity of free space, permittivity of vacuum, permittivity of free space, we say. In the sense, how much permission the medium is giving to attract the two charges or to repel the two charges, how much permission the medium in between the two charges it is giving, even it depends, the force depends on that also. How much permission the medium is giving for the force of attraction or for force of repulsion. Okay, so that we say as permittivity. In vacuum, if two charges are separated by some distance, if the same two charges separated by same distance, if we keep in water, the force of attraction or repulsion between them, it decreases 80 times. It decreases 80 times. Okay, so therefore the medium between the two charges also plays a very, very important role. In free space, so this value is 9 into 10 to the power of 9. In any other medium, so then the question will be different. In other medium, if I write the same expression in other medium, this is in free space, in other medium, it will be F is equal to 1 by 4 pi epsilon, we say just epsilon. We write it in this way, epsilon 4 pi epsilon q1 into q2 by d square. If it is in vacuum, we use the suffix here 0. If it is vacuum, epsilon. If it is any other medium, so then we use 1 by 4 pi epsilon q1 q2 by d square. Force is equal to 1 by 4 pi epsilon q1 q2 by d square. Okay, if it is free space, it is epsilon naught. Okay, so now we'll find out the unit for this constant. That is the one of the very important question that they ask. What is the unit of proportionality constant? Write the dimensional formula for this. Okay, and what is the unit of this epsilon naught, permittivity of free space? What is the unit of it? In fact, its value, epsilon naught value is it is 8.854 into 10 to the power of minus 12. In SI, it is 8.854 into 10 to the power of minus 12. Its value, what is the unit? We will find it now. What is the dimensional formula of this 1 by 4 pi epsilon naught? What is the dimensional formula for epsilon naught? What is the unit of epsilon naught? What is the dimensional formula of the for this 1 by 4 pi epsilon naught? Those things we will find out now. So F is equal to 1 by 4 pi epsilon naught q1 into q2 by d square. 1 by 4 pi epsilon naught is equal to what is F into d square divided by q1 into q2. 1 by 4 pi epsilon naught, I can write it as F d square by q1 into q2. Okay, so unit we will find out first. How we measure force Force we measure in terms of Newton. Distance we measure in terms of meter in SI. Newton meter square. So divided by charge we measure in terms of Coulomb and Coulomb. So this will be Newton meter square per Coulomb square. Newton meter square per Coulomb square. So 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. So its value is 9 into 10 to the power of 9 Newton meter square per Coulomb square. Newton meter square per Coulomb square. Okay. So now, what is the unit of this epsilon naught? Permittivity, which is 8.854 into 10 to the power of minus 12. What is the unit of that? We will find out. Say 1 by 4 pi epsilon naught. Its unit is Newton meter square per Coulomb square. So 4 pi does not have any unit. So therefore epsilon naught is inverse of this unit of epsilon naught, since it is inverse 1 by epsilon naught is equal to this. Epsilon naught is equal to, it is a Newton meter square per Coulomb square. So unit of epsilon naught, I can write it as exactly inverse of this. What it is? It is a Coulomb square. When it goes up, Coulomb, it becomes Coulomb square per Newton per meter square. Coulomb square per Newton per meter square. This is unit of epsilon naught is Coulomb square per Newton per meter square. As I mentioned, epsilon naught value is 8.854 into 10 to the power of minus 12. It is Coulomb square per Newton per meter square. Coulomb square per Newton per meter square is the unit of epsilon naught. So 1 by 4 pi epsilon naught unit is Newton meter square per Coulomb square. So in that permittivity, permittivity unit is Coulomb square. It is exactly inverse of this. Coulomb square Newton, Coulomb square per Newton per meter square. Now writing the dimensional formula for this. So what it is? Dimensional formula for force. It is 1 in mass, 1 in length, minus 2 in time. 1 in mass, 1 in length, minus 2 in time. So whereas this is a 2 in length. Charge. What is the dimensional formula for charge? So, current is taken as a basic unit. Current is taken as a basic unit in our current electricity part. Hmm? So, I is equal to, it is Q by T. Therefore, Q is equal to I into T. So, dimensional formula for Q is equal to, it is 1 in current, 1 in time. 1 in current, 1 in time. Dimensional formula for charge is 1 in current. We write it as A, but while reading, while reading we take it as current. Even in place of A, you can write I also. In few of the book, they have mentioned it as I. But whatever it is, either you use A or I. But when you are reading, you have to read it as 1 in current, 1 in time. That is the dimensional formula for charge. So this will be 1 in current, 1 in time, 1 charge. Other charge, 1 in current, 1 in time. So this will be mass, 1 in mass, 3 in length. Okay, so this length and this length. So minus 2 here, and these are T, if they go up, minus 4, and this is minus 2. So this will be dimensional formula for 1 by 4 pi epsilon naught. Dimensional formula for the constant is 1 in length, 1 in mass, 3 in length, 1 in mass, 3 in length, minus 4 in time, and minus 2 in current. So that itself, if I write a dimensional formula for epsilon naught, this for permittivity, see, these two does not have any dimension. These two does not have any dimension. So epsilon naught, dimension of epsilon naught is exactly inverse of this. What it will be? Exactly inverse of this, because 1 by epsilon naught, it is exactly inverse of this. What this will be? Minus 1 in mass, minus 3 in length, 4 in time, 2 in current. Exactly inverse. So now dielectric constant, or it is also called as relative permittivity. Dielectric constant or relative permittivity. What does it mean by this? Dielectric constant of a medium, or relative permittivity of a medium. See, when I apply Coulomb's law in free space, so this will be 1 by 4 pi epsilon naught q1 into q2 by d square. What it is? In free space, in vacuum, in a free space or in vacuum, it is F is equal to, I can write it as force in vacuum, 1 by 4 pi epsilon naught q1 q2 by d square. Okay. The force in a medium, I will write it as 1 by 4 pi epsilon, only epsilon. Force in a medium, it is 1 by 4 pi epsilon. Same charges, q1, q2, separated by same distance. Okay. So this is initially two charges, q1 into q2 separated by distance d. Same charges q1 and q2 separated by the distance d, but now these two charges are placed in a medium. In a medium we have placed. This is placed in vacuum. This is placed in medium. It is placed in medium. So then, so this will be 1 by 4 pi epsilon q1 q2 by d square. If you take the ratio of these two, in a sense, when we divide these two, what is this? q1 q2 get cancels, this d square get cancels, this 4 pi and this 4 pi get cancels. So what it is? Fv by Fm. Fv by Fm will be, it is epsilon by epsilon naught. Fv by Fm is, it is epsilon by epsilon naught. So this ratio of epsilon by epsilon naught, this ratio of epsilon by epsilon naught, so this ratio we say it as dielectric constant. We denote it by K. Or this also can be written as relative permittivity, epsilon R. We can write it as epsilon R. Epsilon by epsilon naught, ratio of permittivity of the medium, ratio of permittivity of the medium to the permittivity of a free space. Permittivity of the medium to the permittivity of a free space. So that ratio we say it as dielectric constant. That ratio we say it as dielectric constant or relative permittivity, relative permittivity of that medium, or even the dielectric constant we can define in terms of force also. We can define it in terms of force also. What it is? It is the ratio of dielectric constant is the ratio of force of attraction or repulsion between the two charges separated by certain distance. Separated by certain distance. To the to the force of attraction or repulsion between the same two charges separated by the same distance, kept in that medium, kept in that medium. So this ratio also we said as dielectric constant. In two different way we can define it. It is the ratio of, first is it is the ratio of permittivity of the medium, dielectric constant, or relative permittivity of a medium is the ratio of permittivity to the permittivity of a free space. Permittivity of the medium, ratio of permittivity of the medium to the permittivity of a free space or permittivity of vacuum. Or in other way, in terms of force, how we can define? Dielectric constant or relative permittivity of a medium is the ratio of is the ratio of force of attraction or repulsion between the two charges separated by certain distance to the force of attraction or repulsion between the same two charges separated by same distance placed in that medium. Fv by Fm is equal to dielectric constant. Fv by Fm is a dielectric constant. Epsilon or epsilon naught is our dielectric constant. So dielectric constant, how we can write? So this, if I take it like this, epsilon is equal to, if I cross multiply, it is k into epsilon naught. Permittivity of a medium, permittivity of a medium is equal to dielectric constant into epsilon naught. Dielectric constant into epsilon naught. Okay. Or in terms of this, if I want to write, in terms of this force, if I want to write, how it will be? See, Fv by Fm is equal to K. Okay. So then, what it will be? If I want Fm, Fm will be Fv by K. Fm is equal to force in medium is equal to one of the very important relation it is. Fv by Fm is equal to K. K r epsilon r. Relative permittivity. Either we write it K or epsilon r. So Fm is equal to Fv by K. So how can I write this? Force in a medium. is equal to Fv. I will write it as 1 by 4 pi epsilon naught. It is Q1 into Q2 by R square whole divided by K. So this I will write it as Fm is equal to, in a medium, force in a medium is 1 by 4 pi epsilon naught into K. Into K. It is Q1 into Q2 divided by D square. In place of epsilon, you are substituting it as epsilon naught into K. So force in a medium is 1 by 4 pi epsilon naught K into Q1 Q2 by D square. So now, so Coulomb's law, what are the limitations of Coulomb's law? What are the limitations of Coulomb's law? The first limitation is you can apply this Coulomb's law only when the charges are at rest. When charges are at rest. You can apply Coulomb's law when the charges are at rest. If they are moving, you cannot apply. You can apply, you can find the force between them only if they are at rest. So then, second, as I mentioned, they should be point charges. The charges what you are to which you are applying Coulomb's law, the charges should be point charges. The charges should be point charges. If there is an extended charge, if it is extended charge rather than being a point mass, if it is an extended charge, then the separation between the two charges must be very large. Compared to their size of the charge, the separation between them should be very, very large. Okay, you are applying them to point charges. Of course, it is. You are applying them to point charges. Okay, if it is not a point charge, if it is an extended object like this, extended charge like this, so then the separation between those two charges must be very large compared to the size of them. Okay, Next, third point. The range of Coulomb's law, the shorter range of the Coulomb's law will be to the extent of 10 to the power of minus 15 meter only. Nuclear size, you may remember, it is nuclear size. The range will be to this extent only. If less than 10 to the power of minus 15, the nuclear force becomes very strong. So nuclear force exists there between the two charges. Up to 10 to the power of minus 15, you can see these Coulombian force between the charges. That's what I mentioned. There is a Coulombian charge between nucleus, which is positively charged, electron, which is negatively charged. There is a Coulombian force of attraction between those two. But inside the nucleus, if you go inside the nucleus, so there we won't find this Coulombian force. Nuclear force dominates here. Because of that, protons, though which are positively charged, many number of protons are present in the nucleus. Many number of protons are present in the nucleus, depending on their nuclear mass, all those. But still, all those are held together in that tiny nucleus. In fact, positive and positive like charges, in fact, according to our Coulomb's law, they have to repel each other. Protons has to repel each other. Because a proton and a proton which is positively charged, like charges repel. But inside the nucleus, nuclear force dominates. Nuclear force exists. Coulombian force does not exist there. So, to what range you can observe? Till to the 10 to the power of minus 5 it exists. Coulombian force, electrostatic force exists. Less than that, you cannot see. So therefore, range of the Coulombian force is to the extent of 10 to the power of minus 15 meter. Less than that, the Coulomb's law you cannot apply to that. So that is why, though the protons are present in the nucleus, they are not repelling each other, they are not moving away from one another. The reason behind this, Coulombian force does not exist at the range of 10 to the power of minus 15. Okay, so these are, anything greater than this, you can apply the Coulombian force. So these are the limitations of Coulomb's law. One of the very important question for your theory point of view. Even state and explain Coulomb's law, that also a very important question. Even this limitations of Coulomb's law is also one of the very important question. So one more important question we will discuss in the tomorrow's class, that is vector form of Coulomb's law. Vectorially, how can you write this Coulomb's law? That we will see in the tomorrow's class. Okay, thank you.